nothing beats, it's time to talk about limit laws for sequences. At least the first couple of basic ones, and then we'll get more advanced in another video. So let's talk about these limit laws for sequences. Okay, question. Are the limit laws of sequences any different than those for the limits at infinity for real valued functions? We've hinted at this before, and you may suspect what the answer is. Nope, they're not any different. So that's nice, because all the other limit laws we know for limits at infinity for real valued functions going to apply. Let's just consider that we have a function f, so that f of k is ace of k. So in other words, f of k is the explicit formula for ace of k being some natural number here. Then, if the limit as x goes to infinity of f of x is L, where this function over here is the real valued function, you know, like for instance, it's some arctangent function or something where the inputs are real valued numbers and they go over real valued intervals. Then, if that happens, the limit of the sequence is L as well. This is because that k, being strictly a natural number, comes from a subset of the real valued numbers. So in other words, we just look at the limit as the input goes to infinity in general, and it's the same old story. And that's what I just said. The sequence itself is a subset of the range of the function f. In other words, because the inputs k are a subset of the domain of f, x, then we should expect that the outputs for the sequence ace of k is a subset of the range of the values of functions f. Hence, all the same limit properties from real valued functions apply as well. And let's be more specific about the ones we're talking about right now in this video, some of the introductory ones. Let's assume we got two sequences, a sub k and b sub k. And those sequences correspondingly have limits L1 and L2, whatever they might be. Then, under those assumptions, of course, L1 corresponding to a sub k and L2 correspond to b sub k, then we get, well, limit of the sum of two sequences is the sum of the limits. That's that first limit you see right there. The limit of a constant, a real value constant times a sequence, is the same as just the limit of the sequence, a sub k, times that constant, the constant multiply rule. Both these first two properties, same as real valued functions. What about if you have a product of two sequences? Well, the limit of that product is the product of the limits. Same as for real value functions as well. And then finally, if you have a quotient of two sequences, then that limit of that quotient should be the same as the quotient of the limits, L1 over L2, assuming that the limit of b sub k is non-zero. That's what we're calling L2. So this is all the same stuff that we saw for real valued functions back when we first talked about limits. Same thing. And so hence the questions we may ask for the time being is, well, let's go find some limits. Well, it's just going to be the same kind of thing as doing regular limits from back in the day. So for instance, let's do a couple of examples. Let's find the limit of each of the following sequences. We're going to look at some abstract ones here a little bit to some extent, and this is more to remind us about how the limits work, because it might have been a while. Let me take a sip. So good. All right. So this first sequence we got here, find the limit. That means as k goes to infinity of the sequence defined by the explicit expression here, this function k over k plus 7, that whole thing, to the kth power. Now, what we're really trying to do, just find the limit of this sequence. So limit as k goes to infinity of k over k plus 7 quantity to the k power. That's what we're trying to figure out. So really, like I said before, it comes down to remember all your stuff by limits from previously. So this one, as k goes to infinity, notice that the input here, the inner function that is, that's just going to go to 1. And then as k goes to infinity, well, k goes to infinity. So what's this go to? It goes to 1 to the infinity. And that's an example of an indeterminate power. It's not an indeterminate form, but what it means is we can do some kind of stuff, some algebra stuff, so that we could put this into indeterminate form and eventually find the limit. So for the time being, we're just going to assume this limit exists, because if it doesn't, we'll find out. So let's just let the inner function there, let's just call it y, be k over k plus 7 quantity to the k power. Then what follows is that if I took the limit as k goes to infinity of y, well, that's just the same as saying the limit k goes to infinity of our stuff that we're originally looking at. So we're just kind of keeping track of this function because we want to do something to it now, and that is keeping in mind that logarithmic functions are one-to-one functions, they're invertible. Then it should follow, while also including the properties of composition functions, that the limit k goes to infinity of the natural log of y is the same as limit k goes to infinity of natural log k over k plus 7 quantity to the k. Now, remembering all of our properties of logarithms, the advantage of writing this, you might be wondering, is that, well, now we can say that the limit is k goes to infinity of the natural log of y, natural log of the limit we're talking about here, same as natural log k goes to infinity of the limit of y. Whoop, let me rewrite that, I'm sorry. Limit of y, which is the same thing as writing limit k goes to infinity k times natural log of k over k plus 7. And that's it, right? So in other words, we're utilizing the property of logarithms to bring down that k. Why does that help? Don't look at that next example yet. Because now when we write it in this form, this is the same thing as having the form infinity times, well, natural log of 1, which is 0. That is an indeterminate product in which we could then rewrite as an indeterminate form and apply L'Hopital's rule. So that's what we're going to do. We're going to rewrite this now as the same limit k goes to infinity, of course, of, well, we can choose to divide by the reciprocal of one of those factors in the product. I'm going to choose to divide by the reciprocal of k. So I'm going to write this as limit k goes to infinity of k over k plus 7 over 1 over k. It's the same thing. Dividing by the reciprocal is the same as just multiplying by that factor in general. Now it has the form 0 over 0, in which I can apply L'Hopital's rule. I'll apply it, denoted by the big H, as, well, take a derivative of top and bottom. I'll take that limit, right, not a quotient rule. And the limit k go to infinity after we take the derivative of the top function, well, just apply your quotient rule, and what you'll end up getting is 7 over k times k plus 7. And then on the bottom, derivative of 1 over k, that's negative 1 over k squared. Does this help? Yep, sure does. Because now that limit we can say is the same as -7. How did I get that? Well, just redistribute that -1 over k squared in the denominator. That negative k squared goes to the top, and we have a -7k squared over k times k plus 7, which by rational functions converges to -7. Hence, that's not an answer, because the actual answer, remember, this is the natural log of the limit. So in order to get the limit is k goes to infinity of just y. We got to exponentiate that, e to the -7. So there you go. So you see, we just found the limit of this sequence. This sequence, plug in k is 1, plug in k is 2, plug in k is 3, boom, boom, make a list, right? Well, that limit is going to have the same limit as if you let k go across all real numbers, starting at 1, boom, 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 all the way to real numbers towards infinity. It's going to be the same thing, and we just did the same thing that we would do as if it was a real valued function. E to the -7 is the limit. Now, for the last example, just to recall, this might be a little less involved. This limit right here, what we're looking for, limit k goes to infinity of this sequence that we have, natural log 1 over k over k. So let's think about what this happens here. As k goes to infinity, the numerator is going to go to, well, natural log of 0, which is going to approach -infinity. K goes to infinity in the denominator, that goes to infinity. So that is indeterminate form, and hence we can just go ahead and directly apply L'Hopital's rule. And applying L'Hopital's rule, we get limit k goes to infinity of derivative of natural log 1 over k. So that's using the chain rule, we're going to end up getting, if you go through it, a -1 over k, and then derivative of k is just 1. So as k goes to infinity here, this just goes to 0. So there you go. Just say, what we're going to do when we talk about limits of sequences, we're going to do the same thing. So when we talk about limits of regular old real value functions across intervals of real numbers. That's the end of what I wanted to talk about in this video. But then what comes next is a little more terminology, ways of describing the behavior of sequences so that we can use other theorems to quickly conclude whether they converge or not. So that's it. Hope it helped, maybe even review limits. The end. Bye-bye.